Hello everyone. Today we are going to study chapter 7, estimating parameters and determining sample sizes. Firstly, let me go ahead and show you these are four sections that we are going to study in this chapter. Section 7.1, estimating a population proportion. Section 2, estimating a population mean. And 3, estimating a population standard deviation and variance. And the last one, bootstrapping using technology for estimates. So firstly, let me go ahead and give you an example for estimating a population proportion. So let's do this example together. If you want to estimate what percentage of all college students drink coffee daily, since it's not feasible to ask every student, you collect a sample, right? So given the sample size n equals 200 and the number of students who drink coffee daily, number of students who drink coffee daily, we have 130. Okay, and the confidence level is 95%. 95%. Okay, so now let's get started. We do it step by step. If you want to construct the confidence interval, right? Because in this case, we need to find like we are 95% confident that is between that's gonna be um, between p hat minus the margin of error and the p hat plus the margin of error, right, of all college students drink coffee daily. So we need to calculate the sample proportion first. How do we calculate the sample proportion p hat? Calculate sample proportion p hat. We have p hat equals 130 divided by 200, right? 130 divided by the sample size. It gives us 0.65. The second step, we need to compute the standard error. The standard error, I'm going to denote it as SE. So based on the formula for the standard error, we have standard error equals square root of p hat times 1 minus p hat divided by n, right? So it gives us when you plug pH, what do we have? We have 0.65, right? Times 0.35 because 1 minus 65 gives us 0.35 and n is 200. So it approximates 0.0339. Okay, so this is the standard error. The standard error tells us how much the sample proportion varies from sample to sample, right? Now, we need to do the third step, find the critical value for 95% confidence. Okay, we find the critical value for 95% confidence. Okay, since this is a proportion and sample is large, right? So we use the standard normal distribution or Z distribution. So we will find the critical value Z star is 1.96 Do you still remember how to calculate z star in this case? Okay, I'm gonna record it. Okay, so if you want to calculate z star in this case, you can do the method. You can use the z table, the standard normal table, or you can use calculator or technology. The TI-84 calculator can gives you the z star, or you can use Excel with some function or Python as well. There are several ways to do it, and let me show you. Okay, I'm gonna remove this one, move to trash. Okay, I'll use this one. Okay, if you want to use the z table, the normal method, right, for a 95% confidence level, the area between negative z star uh, and z star, a negative z star and z star is 0.95. Do you agree with me? So that means the error to the left of z star will be 1 plus 0.95 divided by 2. It gives us 0.975, and this is the area to the left of z star. Are we good? So now let's look up 0.975 in the z table. Then you can see, if you look at the table, I have the table in front of me here. Let me share the screen then. Replace current share. Okay, maybe allow. Yeah, I'm gonna share desktop 3. Can you see the screen now? Let me look at the Zoom. Okay, Z. Let's look at this one here. Okay. This is the Z. Oh, okay. If you look at this table, let's look at 0.975, right? 0.975. Where is it? Right here. Can you see that? I'm gonna use the pencil. 975 right here. So it corresponds to this row in this column. The z score will be 1.9, and then right here we have 6, right? 1.96. Are we good? Okay, then I'm gonna go back to the uh, good notes, and then we can continue this example, right? So we have z star equals 1.96 based on the table. Okay, if you use a calculator like TI, sorry, 84 calculator, um you can use this one, norm, and then 0.975. It gives us the result for z star. Or if you use Excel, you can use norm, the function norm dot s dot NIV 0.975. Okay, and if you use Python, you can check Python. You can check this one, norm dot ppf 975. Okay, so this is how we can find z star from the 95% confidence level. Are we good? Good, right? Okay, so the next step, the step number 4, we need to calculate the margin of error, or you can denote it as ME, the margin of error. The formula for the margin of error equals z star times the standard error, right? It gives us 1.96 multiplied by 0.0339. That's what we calculated it earlier here, 339 in the step number 2. So it's gonna give us 0.0665. This is the margin of error. And then the last step, construct the confidence interval. So we have the confidence interval is pH minus ME to pH plus ME, right? Then you can find the confidence interval. And this one is gonna be 58.35%. This one will be 71.65%. So when you do the interpretation, it means we are 95% confident that between 58.35% and 71.65% of all college students drink coffee daily. So that is the meaning of this example about estimating a population proportion. Are we good, everyone? Okay, so let me go ahead and share the screen on my laptop because this one is a bit the 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 letter is a bit weird here with the form. Maybe it's because I sent it using PowerPoint form. Let me share. I'm gonna do stop sharing here, and I will share the screen from my laptop. Okay, Zoom. Stop sharing. Okay, share desktop one. Can you see it here, everyone? So the key concept here, this section presents methods for using a sample standard deviation S or a sample variance, right? Let me go back to the screen. To estimate the value of the corresponding population standard deviation or population variance sigma squared. Here are the main concepts. So the point estimate, the sample variance S squared is the best point estimate of the population variance sigma squared, and the confidence interval. When constructing a confidence interval estimate a population standard deviation, we construct the confidence interval using the chi-square distribution. We just calculated the confidence interval from the previous example, as you can see. Now, what is the chi-square distribution? So we can do it using the chi-square distribution as well, right? Key points about chi-square distribution is in a normally distributed population with variance sigma squared, if we randomly select the independent samples of size n, and for each sample, compute the sample variance S squared, the sample statistics chi-square equals n minus 1 times S squared divided by sigma squared, has a sampling distribution called the chi-square distribution as shown in the formula 7.5. So you can see that in the book, and that is the formula down here. Chi-square equals n minus 1 times S squared divided by sigma squared. And the critical values of chi-squared, we denote a right-tailed critical value by chi-square R. R stands for right-tailed, and we denote the left-tailed critical value by XL squared. Those critical values can be found by using technology or table A4, and they require that we first determine a value for the number of degrees of distribution, right? So in this case, what is the degrees of freedom? Degrees of freedom for the methods of this section. The number of degrees of freedom is the sample size minus 1. So we have df is n minus 1. That's the formula for the degrees of freedom. So let's do an example, right? Maybe you can understand it better. The chi-square distribution is skewed to the right, unlike the normal and the student t distribution. Okay, this is not symmetric at all, and all values are non-negative here. And the values of chi-square can be 0 or positive, but they cannot be negative. You can see it's above the x-axis, right? That's the chi-square distribution. And the chi-square distribution is different for each number of degrees of freedom. As the number of degrees of freedom increases, so you can see here, it increases. So df is 20, right? The chi-square distribution approaches a normal distribution. So the shape is similar as a bell shape and is more symmetric comparing to the red one here. Now let's move to the next one. The caution, because the chi-square distribution is not symmetric, a confidence interval estimate of sigma squared does not fit a format of s squared minus e and s squared plus e. So we must do separate calculation for the upper and lower confidence interval limits for this chi-square distribution instead of the normal distribution, right? We can find like one of them and the other one will be symmetric. So it's very easy. Now, for the chi-square distribution, we have to use table A4 for finding critical values instead of table A2 like we did in the previous example. And note that the following design feature of that table, each critical value of a chi-square in the body of the table corresponds to an area given in the top row of the table, and each area in that top row is a cumulative area to the right of the critical value. Now in this case, remember it's the cumulative area to the right, not the area to the left of the critical value, right? In the table A2 for the standard normal distribution provides cumulative area from the left here. This is just the recall, right, from the previous chapter. But table A4 for the chi-square distribution uses cumulative areas from the right. That's the main difference. And now this is an example for finding critical value of chi-square. A simple random sample of 22 pulse rates is obtained. Construction of a confidence interval for the population standard deviation sigma requires the left and right critical values of chi-square corresponding to a confidence level of 95% and a sample size of n equals 22. Find the critical value of chi-square separating an area of 0.025 in the left tail and find xr squared, the critical value of chi-square separating an area of 0.025 in the right tail. So now let's do it together. Let me share the, so that I'm gonna write on the screen here. Oh, it's easy, okay. With a sample size of n equals 22, right? In this case, n equals 22, the number of degrees of freedom, we calculate that one first. df equals n minus 1, which is 21. And look at the shape of the the chi-square distribution. In this case, we have the lower in this case, let's see the upper one, the chi-square, the right tail chi-square will be 35.479, right? And XL square is 10.283. These are from the table A4. That one is similar to table A2, so you can check it. Are we good here, everyone? Here, because the critical value of x of chi-square separated in an area of 0.025 in the left tail, and this one in the right tail. So we know 0.025. Then you can find 10.283 from this number. Okay. Then um, I'm gonna mention, yeah, we can make the conclusion here. The critical value to the right is obtained from table A4 in a straightforward manner by locating 21 in the degrees of freedom column at the left and 0.025 across the top row. You can see this table and then find this number easily. In this one, we must locate, in this case, please remember the area to the right, okay? So we have to take 1 minus 0.20, 0.025 to get this number, 0.975, the area to the right of that XL square. And then now we must locate this number across the top row because the values in the top row are always areas to the right of the critical value. And you can use the degree of freedoms, and also you can use the number 0.975, okay, to get XL is 10.283. Are we good, everyone? Objective here, construct a confidence interval, estimate a population standard deviation or variance. You can, okay, this is for population standard deviation or variance. So let's do it together. If you want to find this confidence interval for estimating a population standard deviation or variance, we must know these notations. The first one is the population standard deviation. Sigma square is the population variance. S stands for the sample standard deviation, and S squared is the sample variance. N here is the number of sample values. E is the margin of error, chi-square. Normally we use like margin of error, ME, right, for the normal distribution, but this one is for chi-square distribution, so we use E only. In the left-tailed critical value of chi-square, normally the critical value of in the normal distribution, we use Z star, right? But in this case, we use we use chi-square here and then L. This one is like chi-square R. R stands for the right tailed. Okay, so now let's move to the requirements. There are two requirements. The first one, the sample is a simple random sample. And the second one, the population must have normally distributed values. And the requirement of a normal distribution is much stricter here than in earlier sections. So large departures from normal distributions can result in large errors. Okay, and there is the formula for the confidence interval estimate for the population variance, sigma squared. We know that sigma square is between n minus 1 times s squared divided by chi-square r. This one is like divided by r square L. The reason is r square L is less than r square r, so when you denote the same number by the larger number, is going to be smaller, right? Okay. In the confidence interval estimate of the population standard deviation, sigma is going to be between these two numbers. So you just need to square the upper level and the the upper number here, right? The upper bound and the lower bound. Then you can get this one is the confidence interval for the standard deviation, because the standard deviation is the square root of the sigma squared above. So that's why. Does that make sense, everyone? Good, right? Okay. Here is the confidence interval for estimating a population standard deviation or variance. Randolph rule. So there are two rules here. The first one, original data. When using the original set of data values, route the confidence intervals limits to one more decimal place than is used for the original data. Any questions so far? Let me see if you have any questions. So far, no, right? Okay. In the second rule, summary statistics. When using the summary statistics, NS route the confidence interval limits to the same number of decimal places used for the sample standard deviation. Okay, let's see the procedure for constructing a confidence interval for sigma or sigma squared here. The first step, we verify that the two requirements are satisfied, the two requirements above, right? The second one, using n-1 degrees of freedom, we find the critical values chi-square R and chi-square L that correspond to the desired confidence level. In the third step, to get a confidence interval estimate for sigma squared, we use the following formula. This is the formula for chi-square, for delta square above. The fourth step, to get a confidence interval estimate for sigma, take the square root of each component of the above confidence interval. Here we take the square root on this side and this side. And then the last step, route the confidence interval limits using the round-off rule. This is the round-off rule, right? There are two rules here. And these are two requirements that we need to check. Are we good? Okay. So if we are good, let's move to the next one. The comparisons here. Confidence intervals can be used informally to compare the variation in different data sets. But the overlapping of confidence intervals should not be used for making formal and final conclusions about equality of variances or standard deviations. Any questions or comments here? Okay, if no, we move to the example, right? Example, confidence interval for estimating sigma for pulse rates. Listed below is a simple random sample of pulse rates beats per minute or BPM obtained from adult females based on data set 1 body data in appendix B. We construct a 95% confidence level, confidence interval estimate for sigma. So this is the data. Now, the first step, we always have to check the two requirements, right? The first one, the sample can be treated as a simple random sample. Yes. Okay. Yes. The second one, the accompanying normal quantile plot suggests that the sample is from a normal distributed population because the points are close to a straight line pattern right here. You can see, right? So it satisfies the normal distributed population. Step number 2, we can use table A4. We use the sample size of n equals 22 to find degrees of freedom. So we know that the degree of freedom is 21. And then we refer to the row corresponding to 21 degrees of freedom and refer to columns with area 0.975 and 0.025 for a 95% CI. We divide alpha equals 0.05 equally between two tails of the chi-square distribution. And we refer to the values of 0.975 and 0.025 across the top row. And then we can use the table to determine the critical values chi-L, chi-square L, and chi-square R. Are we good, everyone? If we use technology, you can also use the we find the confidence interval. Let me show you the table A4, okay? But before that one, maybe we can have a little break, 5 minutes break then. Okay, let me, yeah, I just started recording again after the break. Let me recall what I did earlier. So in this case, this is an example to calculate the confidence interval for estimating sigma for pulse rates, and we have this data. Now we need to follow all the steps to calculate the confidence interval, right? The first step, we check all the requirements. We already finished that one. The second step, we use the table A4. So let me share the table A4 here. Can you see the screen? Chelsea, can you see the table and confirm with me? You can see that?
Yeah, I can see it, no problem.
Okay, yeah, thank you. Okay, so this is the one. Now we look at the degrees of freedom. It is n minus 1, right? The sample size is 22, so df is going to be 21. And now we will check the refer to the columns with areas 0.975 and 0.025 to find the chi-square left and chi-square right. This is the left tailed and this is the right tailed. Based on the, so we have 21, right? df 21 down here, 21, and then 0 chi-square point 975, so it's 10.283. Okay, 10.283. This is the chi-square left, the left-tailed critical value, and this is similarly you can find the right-tailed critical value 35.479. This is done. We are done step number 2, or step number 2. As I discussed earlier in the previous section, you can also use technology. You can use uh, the calculator or even Python. The confidence interval can be found using this way. So you can use the technology like TI-84 calculator, right? Like I did in the previous section. And then you can calculate the 7.6 BPM is the lower bound for the confidence interval, and 14.2 BPM is the upper level. So this is our conclusion. After that, we can I'm gonna mention a little bit about the interpretation. So using table A4, we first use a sample size, right, to find the degrees of freedom, df, and then we will find the areas areas in that table. Areas here is area to the right of the critical value, right? The left-tailed critical value or the right-tailed critical value. And in the normal distribution, when we look at table A2, that's going to be the area to the left of the critical value z star. So that is the difference. And then for 95% confidence level, we divide alpha equals 0.05 equally between the two tails of the chi-square distribution. And we refer the values of 0.975 and 0.025 across the top row of table A4. Now the critical values are the chi-square left equals this one and chi-square right equals that one. Now the next step, based on what we discussed earlier, this is the formula for the confidence interval for sigma square. Okay, we need to use the formula n minus 1 times s squared divided by the right-tailed critical value here. And we know this number, already. We know n minus 1 already. What about s? So s here is a sample standard deviation. And how do we find s? Actually, in this one, we already have we can calculate s based on the formula for the sample standard deviation, right? Based on the data here. And then we plug all the numbers in here to calculate the confidence of interval, the confidence interval. Now the step number 4, when after calculating, you will get the confidence interval is 58.2419 to 200.9495. Now we need to, if you want to find the confidence interval for sigma, you need to square root both sides of these inequalities, right? Then you get 7.6 and 14.2. So this is the conclusion. It use this 95% confidence interval estimate the population standard deviation. Uh, any questions so far?
No questions.
Okay, thank you so much. So
Mm-hmm.
we can do the interpretation like this, and then after that, I'm gonna give you another formula determining sample sizes, and the procedures for finding the sample size necessary to estimate sigma are much more complex than the procedures given earlier for means and proportion, right? For normally distributed population, the table on the following slides or the following formula can be used. This is the formula for the normal distributed population, where D is the decimal form of the percentage error. And we can move to this one. Let me. Do you want me to recall how to estimate a population mean? Maybe we can do that one first before moving to this section. Let me share the screen and then I'm gonna for the sample size. Before doing this one, I'm gonna recall sorry, two more things. Yeah, earlier I gave an example related to this one, estimate a population proportion. Now I'm going to record two more things. The second example related to estimating a population mean, and the third one will be estimating a population standard deviation or variance. And then after that we will move to the determining sample sizes. Blank. Okay, let's do the example related to estimating a population mean. And again, we are interested in estimating the average lifetime of all light bulbs in a certain type. So we have the sample size. Let's do the okay, sample size. We have n equals 25 and sample mean I'm gonna take the sample mean x bar equals 150 hours, and then we have the sample standard deviation. Sample standard deviation s equals 80 hours in the confidence level. %95. Okay, so let's do it step by step, right? The first step, compute the standard error. Standard error, I'm gonna use SE for standard error. And you know the formula is gonna be S divided by square root of N, right? So S here we have 80, square root of N we have 20, square root of 25, which is 5. So we have the answer is 16 is the standard error. Now we need to use the t distribution. Use the t distribution. Since the population standard deviation is unknown, right? And because we just have the sample standard deviation in this case, and we know that n here is less than 30, so we can use the t distribution. That means you need to calculate these two things. The first one is the degrees of freedom, df, degrees of freedom. It is n minus 1, which is 24, right? 24. And we for 95% confidence, we can use from the t table, you can find t equals 2.064. okay, for 95% confidence, t star approximates 2.064. Are we good with this one? Maybe I can give you the explanation in more detail using the table. I'm logging into the table here.
Is it 2.006
Yeah, 2.006.
bar? Yes, it's 6.4. Guys, I was just looking at the table too. I have a table pulled
Oh,
up.
you have the table, right? Okay,
Yeah.
wonderful. Yeah. Okay, good. Then we can move to the next one. Because in the previous one, I also like calculate Z star and I explained it from the table already, but that one is I didn't download the T table here. Okay. Now, if you agree with me, this step, the next step, we need to calculate the margin of error again. Similarly, the margin of error, I'm going to use ME. ME here is T star multiplied by SE, the standard deviation, and I have 2.064 multiplied by 16, and I'm gonna get 33.024. So this is the margin of error, right? We're good. Now we need to construct the confidence interval. The confidence interval formula is X bar minus ME and X bar plus ME, right? Based on the calculations we get, this is the confidence of interval. We have 1116.976 and the other one 1183.024. So we can do the interpretation like this. We are 95% confident the average lifetime of all light bulbs is between 1116.98 and 1183.02 hours, right? So that is the example for estimating a population mean. Is there any questions so far?
No, no questions.
Yeah, very good.
Yeah.
Can you see the screen that I'm writing on my iPad, right?
Yeah, no, I can see it. Mm-hmm.
Okay, okay. I just want to make sure that uh but I cannot like, oh, the recording I didn't show it on the screen. Maybe when I record it will not appear here. So let me I'm I'm gonna show this one here so that when other people see the recording, they will know what I'm writing here. Okay, and then the next example, I'm gonna show you how to estimate a population standard deviation or variance. Let me move this one to the side here. Okay, so again, we can do this. We want to estimate the standard deviation of the life span of all batteries of a certain brand. Let's do this one. We do the sample size n equals 10. We have the sample standard deviation S equals 4.5 and the confidence level 95%. Okay, so let's do it together. The solution, we do it step by step. The first step, we can use the chi-square distribution, right? Because in this case, when estimating variance or standard deviation, you will use the following formula: n minus 1 times s squared divided by divided by chi-square to right tail less than sigma, sorry, sigma, not delta, sigma square less than n minus 1 s square divided by chi-square to the left left tail. Now we will calculate n s and chi-square right, chi-square left, right? The degree of freedom df is n minus 1, which is 9. Done. From the chi-square table, you can find chi-square right and chi-square left. So for chi-square right here, actually it's similar to the previous example, right? Let's check it. together. What do you think?
Sorry, I'm just getting my calculator.
Yeah, because um the middle area, if we want, we are building a 95% confidence interval. That means the middle area is 95%, right? The two tails combined is 5%. So each tail we have 0.5, no, we have 2.5%. Do you agree with me? So each tail, when you have 2.5%, that means you have 0.025.
Yeah.
And the left critical value where 2.5% is to the left of it. That means you need to find the left. So I will replace this one by chi-square 0.025, and the degree of freedom is 9. And the other one, chi-square 2 right critical value. That means where 2.5% is to the right of it. That means you have kind of 0.075. Am I right? No, 975. 975. And then the degree of freedom is 9. Correct? Yeah, because in this case you have 2.5 is to the right of it. Correct? That means 0.025. It seems that but it makes sense because the chi-square values increase to the right. Do you agree with me? In this case, chi-square distribution is not symmetric, so you need two different values, and we have two different values in this case, and we can use the chi-square table. So look at the area to the right equals 0.025, and the degree of freedom is 9. Let me check it real quick. 9, df is 9. So we look at the row, df equals 9. And then for the column,
Like 2.262.
0.025. So I can share this screen right here so that you can see desktop one. Okay, can you see the table with me? df is 9, right?
Yeah.
And then this one it is 19.0. Are we good? So 19.0, right? We approximated 19.0. And then we can find the area to the right equals 0 0.0 0.975 975. Okay, 2.7, right? 2.7. So this one I'm gonna write 2.7. So the left endpoint uses chi-square 0.025. It equals 19, and the right endpoint uses chi-square 0.975 with a degree of freedom 9. So we have 2.7. Please remember that the chi-square error here means the chi-square value such that the area to its right is the number down here. I'm gonna stop sharing. So this one, can you see my screen now? The
Yeah, I
iPad
can see
screen.
it.
Okay,
Mhm.
this is if I write like chi-square alpha df, right? It means that the area to its right is alpha. Look at this one, it's alpha. Now let's think about this one. The next step is we need to we need to use a formula here. Calculate the variance bounds. S square, we know that one, right? Because we know S is 4.5 already. So S square is uh, 20.25. Now we plug it back into the formula. So the lower bound, we have the lower bound is 9.6 here. And let me use another color. This one is 9.6 after plugging all the numbers, and this one will be 67.5. But if you want to find the bounds for the standard deviation sigma, then we need to square root both sides. So square root of 9.6, which is 3.1, and square root of 67.5 will be 8.2. So we are done. So this means we are 95% confident that the true standard deviation of battery lifespan is between 3.1 and 8.2 hours, right? Are we good?
Yes. Yeah, no, that's good. So I was
Yeah,
like,
yeah, okay. Yeah, wonderful. So now let me share the screen right here. I'm gonna share desktop one. Okay, so this one is determining sample sizes to be 95% confident that S is within 1%, 5%, 10 percent, and 50 until 50% of the values of sigma the sample size, and should be at least. So we have all this data, right? This is the table. It helps us to determine with all these values. Okay, this one, the difference between this table and the above table is to be 99% confident that S is within these percentages of the values of sigma the sample size, and should be at least this one many. In this case, the confidence of interval will be changed from 95% from the previous table, right, to 99% in this table. And then in this case, with star disk, select analysis sample size determination and then estimate standard deviation. You can use it in Excel or the normal calculator. Oh wait, the normal calculator do not provide such sample sizes, so you just can use
yeah, I've been using that TI 84.
star disk.
Better.
Uh-huh. Yeah, this one do not
That
provide
crunch
such.
is actually really good.
But it helps you with the other critical values, right, and areas under to the left of the critical value for the normal distribution, right? And with the, I think with the chi-square distribution, it helps as well. Sample, finding sample size for estimating sigma. We want to estimate the standard deviation sigma of all birth rates of adult women. We want to be 99% confident that our estimate is within 9% of the true values of sigma. How large should the sample be? Assume that the population is normally distributed. This one, like from the table above, right, from the table that we see, we can see that like 99% confidence in an error of 5% for sigma correspond to a sample size 1336. um if you can see here, 1336, look at this one. That one is 99%, right? So it should be this table. And look at this value. It's going to be in the second row, right? Okay, so based on the table, we can make this conclusion, and we should obtain a simple random sample of 1336 birth rates of adult women. So let's move to the um, PowerPoint of 7.2. I'm gonna do 7.2 here. Okay, zoom in, share desktop one. So this is the second section in chapter 7, estimating a population mean. As I gave you the example earlier, to estimate the population mean, we know how to do it using like the 4 steps, right? And let me go ahead and give you all the definitions of the key concepts in this section. The main goal of this section is to present methods for using a sample means X bar to make an inference about the value of the corresponding population mean mu. And there are three main concepts included in this one. The point estimate. The sample mean is the best point estimate or single value estimate of the population mean mu. Or we can move to the second concept, confidence interval. We use sample data to construct and interpret a confidence interval estimate of the true value of a population mean mu. And the sample size, find the sample size necessary to estimate a population mean. We need to find these three things, and the objective, construct a confidence interval used to estimate a population mean. That's what we just did earlier for the normal distribution, normal distributed, right? Confidence interval for estimating a population mean with sigma not known. We must know all these notation first. Mu here is the population mean, X bar here is the sample mean, S is the sample standard deviation, N is the number of sample values, and E here is the margin of error. You can use ME for the normal distributed normal distribution. Okay, so is everything clear so far?
Yes, no,
Yes, right.
everything's clear.
Yes, yeah. So there are two requirements that we must check before each problem, right? If you want to find the confidence interval for estimating a population mean with sigma not known, we need to check these two requirements. The sample is a simple random sample, and either or both of these conditions are satisfied. The population is normally distributed, or n is greater than 30. If it's less than 30, we use the method that we did in the previous example that I just showed you. Now, in this case, we use the formats X bar minus the minus E, right? The margin of error, and X bar plus E. This is going to be the lower bound and the upper bound for the confidence interval for estimating population mean. And the margin of error E here is will be calculated by T alpha over 2 times S divided by square root of N. This is what we is similar to the previous example, right? We did it because S over square root of N here it is exactly the standard error in the previous example, right? And T alpha over N here, we can find that from the table. The confidence level, the confidence interval is associated with a confidence level such as 0.95 or 95%, and alpha is a complement of the confidence level. For a 0.95 or 95% confidence level, alpha is 0.05, because we take the complement, right? 100% minus 95%, it gives you 5%, which is 0.05. And the critical value in this case, okay, the critical value T alpha over 2 is the critical value T separating an area of alpha over 2 in the right tail of the student T distribution. And the degrees of freedom, we know like it's going to be df is n minus 1 is the number of degrees of freedom used when finding the critical value. Now we move to the round off rule. This is for the last step to round off the number, right? Original data. When using an original set of data values, round the confidence interval limits to one more decimal place than is used for the original set of data. And the second rule, summary statistics. When using the summary statistics of n, X bar and S, round the confidence interval limits to the same number of decimal places used for the sample mean. So in this case, let's check all the formula for the student T distribution. A population has a normal distribution, then the distribution of T will be calculated by this form. Now, this is a student T distribution for all samples of size n. And a student t-distribution is commonly referred to as a t-distribution. Right? We remove like the student, and we just say t-distribution. And the other one is chi-square distribution, right? Okay. Now let's see how to calculate the degree of freedom. In this case, finding a critical value requires a value for the degrees of freedom, df, and df is normally just n minus 1. In general, the number of degrees of freedom for a collection of sample data is the number of sample values that can vary after certain restrictions have been imposed on all data values. And this one is also the method to calculate the degrees of freedom in chi-square distribution as well. So we know like that's going to be the formula for those two distributions. For the distribution, I'm opening the t table for our next example, okay? Because we are gonna use that one later. Okay, so the next one, finding critical value T alpha over 2. A critical value T alpha over 2 can be found using technology or table A3. We know A2 and A4 already, right? Now we are using table A3. Technology can be used with any number of degrees of freedom, but table A3 can be used for select numbers of degrees of freedom only. Because in the table they can write like many things in more detail, so you can use the calculator. Is going to be more convenient if using table A3 to find a critical value of T alpha over 2, but the table does not include the exact number of degrees of freedom. You could use the closest value, or you could be conservative by using the next lower number of degrees of freedom found in the table, or you could interpolate, so we can approximate it, right? Because like in the table A3, we just have the degree of freedom from 1 to 3 until like 30, but after that they skip from 30 to 39, they skip. We just have 40, 60, 80, 100, and then 1000. So that's why it's better to use technology. And the student t distribution is different for different sample sizes. We can see the figure for case 3 and n equals 3 and n equals 12 here. So if n equals 3, look at the sample size, less sample is n, which is less than 12. So the distribution is going to be lower, right? The value right here is going to be lower than this one. Then the standard normal distribution, look at this green one, is going to be the highest one. And for the chi-square error, we don't have the symmetricity, right? So those are the differences. And the key points about the student t distribution: the student t distribution has the same general symmetric bell shape as the standard normal distribution, but has more variability with the wider distributions. It's lower, wider, as we expect with small samples, correct? Because for the standard normal distribution, you can have like the large n, right? But in this case, you have small n. The student t distribution has a mean of t equals 0, just as the standard normal distribution has a mean of z equals 0. The standard deviation of the student t distribution varies with the sample size, but it is greater than 1. Unlike the standard normal distribution, we have the standard deviation equals 1. But in this case, we have sigma is greater than 1. And as the sample size n gets larger, the student t distribution gets closer to the standard normal distribution. Look at this one. The red one is it is approaching the green one here, right? Which is the standard normal distribution. So when n is larger and larger, then it is approaching to the standard normal distribution. Now let's consider the procedure for constructing a confidence interval for mu, and then we can work on an example together. 1. Verify that the two requirements are satisfied. The sample is a simple random sample. and the population is normally distributed, or n is greater than 30. Q, with sigma unknown, as usually it is usually the case, then we can use the formula for the degrees of freedom n minus 1, and then you can use the technology or table A3 to calculate the critical value T alpha over Q that corresponds to the desired confidence level. And the third step, we evaluate the margin of error. We use this formula, right? T alpha over Q times the standard that one is the standard error. In the step number 4, using the value of the calculated margin of error E and the value of the sample mean mu, we substitute those values in one of the formats of the confidence interval. So we know that these are this is the lower bound, this is the upper bound for the confidence interval. And the last step, we route the resulting confidence interval limits as follows. With an original set of data values, we route the confidence interval limits to one more decimal place than is used for the original set of data. But when using summary statistics of n, x bar, and s, we route the confidence interval limits to the same number of decimal places used for the sample mean. So these are like two routing rule that we have seen earlier, right? Now let's consider an example together. Finding a critical value T alpha over Q. Okay, so let's find a critical value in this case. Can you see the example on the screen here, Chelsea?
Yes.
Yes, right? Okay, so we need to find the critical value corresponding to 95% confidence level, given that the sample size is n equals 6. Because n equals 6, the number of degrees of freedom, we know that is 5, right? Because we need to use a table. So anyway, we need to find the degrees of freedom first. And then the 95% confidence level corresponds to sigma is 0.05. So there is an area of, in this case, you can find there's an area of 0.025 in each of the two tails of the t distribution, correct? Because you, like for example, 5% for the two tails divided by 2, you will have 2.5 each. That means 0.025 in each of the two tails here. Now we look at we can use technology. It's going to be faster because the degree of freedom here is 6, right? Let me check the table. Okay, we have 6. It's good.
Yeah. Yeah. That's what I say on the table for, well,
Yeah, yeah, an area of 0.025 in each tail. So the critical value would be, let's check it together. 0.025.
0.025.
I don't have 0.025 here because maybe this table it doesn't have. Oh, here I use two tails.
Yeah, I saw that because I was like, mine is split up in 1 to 2 tails, and
yeah, I can use one tail, maybe one tail or two tails. Are you using the table data tab.net?
I'm just using, I just from the I'm sorry, I just kind of Googled this one from table 3.
Mm-hmm.
And so we're looking at for 6 degrees of freedom for 0 to 5.
6, yeah, is a degree. 5 is a degree of freedom. 5.
Yeah, and then I have
T
0.571
0.025.
for 5.
0. I don't have this one on my table. My table doesn't have that information. I think I have to use
Yeah, I had to Google the T distribution table, well, table
yeah,
A3.
uh-huh. Agree. Okay. 0.25 90. 95%. 0.25. Here we go. 9. Oh, I found it. Okay. I'm gonna share. I think you can see my screen here, right? This is the table that we can use. This is the degree of freedom 5, and look at this one, 2.571. Are we good?
Yep, that's what I got.
Yeah, I got the same. Okay, 2.571. That's what they got as well. Okay, we got it. So to find the critical value using this table, we use this column with the area. Blah, blah, blah. Okay, we did it and we found this one. So that is the critical value. So now the next step we need to do is we can make the conclusion, because in this case they just need to find the critical value. They don't need us to build the confidence interval, so we can skip other steps. It's fine. Now let's do another example. Confidence interval. Now is the time for us to build the confidence interval using peanut butter cups. We know this data, right? And they are from a package of 38 cups, and the package label states that the total weight is 12 or let me see, this one 340.2 grams. The 38 cups have the total weight of 340.2 grams. Then the cups should have a mean weight. Okay, we have the mean weight. Now let's use the listed sample data to find the point estimate of the mean weight. Okay, that means in this case we need to find the sample mean. Do you agree with me? X bar. So if you want to find the X bar, we already have it in the data. It is 8.8. You can find the sample mean here from this data. Are we good?
Yeah, we're good. The
Yeah.
8.8
This
verified.
one, yeah, we just use calculator. So I'm gonna skip that step because that one is easy. We
Easy,
just
yeah.
use calculator to find 8.8057 grams. And then the requirement checks. This is gonna be the first step to build the confidence interval. We check if whether the sample is a simple random sample, and yes, that is the second step, because the sample size is n equals 6, so it satisfies the formula. The population is normally distributed, or the sample size is greater than 30. This one can be satisfied only if the sample data appear to be from a normal distributed population. So we need to investigate normality. Okay. So in this case, in the accompanying normal quantile plot, the points appear to fit a straight line pattern. So when it fits the straight line pattern, that means the sample data appear to be from a normally distributed population. So this satisfies, it helps us to verify the second requirement. In the previous example, we also did this one. We put all the data here, and then we see if it form a straight line pattern or not. If yes, then that is a a standard normal distribution. Sorry, it form a normally distributed population. Now let's move to the next step. We need to use technology to construct the confidence interval. And we can see the lower confidence interval and the upper confidence interval. In this case, you can use the start crunch to find that one and find the confidence interval. So this is another way to do it. It's faster, right? But if you don't have technology, what should we do? So let's do manual calculation. Okay, so we find the critical value. We found it earlier because this data is like 95% confidence level. So that's why we can find the critical value is 2.571 from table A. It's similar to the previous example that we did with the degree of freedom 5. So that's why find the standard deviation. So we know the standard deviation from the original sample values already, right? And then we apply the formula for the margin of error. This is just like we have T alpha over 2 already, we have S, we have N already, we plug everything in here, we can get the margin of error 0.215589. So that is the formula for the margin of error. Now, the confidence of interval is very easy. We just have x bar minus e and x bar plus e. So we plug it in here and then we find the confidence of interval. Is everything good, everyone? Yeah.
No, yeah, everything's good. Mm-hmm.
Yeah, and then we do the interpretation. So this one is simple. We are 95% confident that the limits of 8.5901 grams and 9.0213 grams, these are the lower and the upper of the confidence interval here, actually do contain the value of the population mean mu. If we were to collect many different random samples of 6 peanut butter cups, um, mini, miniatures, and find the mean weight of each sample, about 95% of the corresponding confidence intervals should contain the mean weight of all such peanut butter cups. So that is the interpretation of the problem. And okay, we noticed earlier that the sample is from a bag of 38 cups, and the bag is labeled as containing the total weight of 340.2 grams. So the mean weight of the cup should be calculated. In this case, we divided it by 38, right? And we calculate the mean of the cup. But the confidence interval limits do contain the desired mean of 8.9, correct? So the package appeared to have been filled with candy in an acceptable way. It should have been better to obtain a simple random sample. Okay, yeah, it makes sense, right? Because this level of confidence here, it contains the 8.9, 8.9 between these two numbers. And the point estimate of mu, we can calculate it using this formula, the upper confidence limit plus the lower confidence limit divided by 2. It gives us the point estimate of the mean. And the margin of error, we can calculate it using the confidence interval. We take the upper bound minus the lower bound divided by 2, and it gives us the margin of error. So they are related, right? All three terminologies, three concepts in this section. Estimating a population mean when sigma is known. In the previous example, did you notice that we don't have sigma? Sigma is unknown. But if sigma is known, we can have a faster way to calculate E, the margin of error. We use Z alpha over 2 times sigma over square root of n. Sigma over the square root of n here is the um, the standard error, right? Correct. And the margin of error equals the critical value multiplied by that one, by that formula, SE. Now we look at all the conditions to choose the correct distribution. The conditions: if sigma is not known in normally distributed population, or sigma not known and n is greater than 30, we can use the T distribution. We use this one to calculate the margin of error, because we don't have sigma. So that's, it makes sense, right? And when sigma is known, we can use this one formula because it appears sigma right here, and this one is normally distributed population as well. And please remember the second case, if n is greater than 30, in reality sigma is rarely known, so we can use the second formula in reality. And when the population is not normally distributed and n is less than or equal than 30, you can use the bootstrapping method. So this is what we are gonna do now. I'm gonna give you an example for this method, and then we can understand how to use the bootstrapping method. Okay. Let's see. Um, that one. Okay. Finding the sample size required to estimate a population mean. Object, we need to determine the sample size n required to estimate the value of a population mean mu. Finding the sample size. So in this case, we need to know all these notations, and we know them all, right? This is the population mean. This is the population standard deviation. This is the sample mean, margin of error, and this is the z-score separating an area of alpha over 2 in the right tail of the standard normal distribution. And then the requirement, now we just have one requirement. This one is a simple, the sample must be a simple random sample. The formula for the sample size, it can be calculated by this way. Okay. And the round off rule here, we just have one round off rule instead of two, like in the previous T distribution. If the computed sample size n is not a whole number, we round the value of n up to the next larger whole number. Very easy, right? And these are Okay, these are the range thumb rule of thumb, and the starting improve one to deal with the unknown sigma when finding the sample size. We use the range rule of thumb to estimate the standard deviation as follows: sigma equals range divided by 4, where the range is determined from the sample data. In the second one, start the sample collection process without knowing sigma, and using the first several values, calculate the sample standard deviation S and use it in place of sigma. The estimated value of sigma can be then improved as more sample data are obtained and the sample size can be refined accordingly. There's another way to deal with that. Estimate use prior results. We estimate the value of sigma by using the results of some other earlier study. In addition, we can sometimes be creative in our use of other known results. And using a value for sigma that is larger than the true value will make the sample size larger than necessary, but using a value for S that is too small would result in a sample size that is in an inadequate. When determining the sample size N, any errors should always be conservative in the sense that they make the sample size too large instead of too small. Okay, that's what we need to pay attention here. Okay, maybe we can do one example to understand it. The example related to IQ scores of statistics students. Assume that we want to estimate the mean IQ score for the population of statistics students. How many statistics students must be randomly selected for IQ tests if we want 95% confidence that the sample mean is within 3 IQ points of the population mean? Okay. So in this case, we know that a confidence level, confidence 95% confidence. That means we have alpha in this case. Let me see. I'm gonna write on the screen here. Okay. Maybe let me move to this one. I'm gonna scroll down. Stop share here. Can you see my screen?
Yeah, I can see it.
Move to the. Okay, this one is the example. I'm gonna write on the screen here. Since we have 95% confidence interval, that means alpha here is 0.05, right? Complement, like 100% minus 95%, we have 5%, which is 0.05. So z alpha over 2, in this case alpha is 0.05, so z alpha of 2.025 equals 1.96, right? This one I did it in the very first example, but I can show it on the screen here. This is from the A2 table. I'm gonna open, I'm gonna share. Okay, look at this one, z 0.025, 0.025. So that one, I think I did explain it in the first example already. So let me, to save time, I'm gonna go back to the first one here. That's what I remember because I did it earlier here. Here, yeah, I calculated it earlier here. For 95% confidence interval, we know that the area between z negative z star and z star is 0.95, right? So if you want to find the area to the left of z star, it's going to be okay. Can you see the screen right now, the one that I'm
No, I can see it.
or maybe you don't see this one. This one, okay, here. That's what I need to show, another table. And I'm gonna find the area to the left of z star, and that is gonna be 1 plus 0.95 divided by 2, so I will get 0.975. And after that, I will use a table. I will use a table to find what is the z value corresponding to the area to the left of z star is 0.975. So this is 0.975, 0.975 right here, right? So that's why I have 1.96. That is the z star. Are we good? Yeah.
Yeah, we're good. I see.
So yeah, so that's why I wrote it, the answer 1.96 immediately. I didn't put more explanation because we did it already. And then let me open another one. And then I calculate, because we want the sample mean to be within 3 IQ points of mu. That means the margin of error in this case will be 3, right? That is the definition of the margin of error. Also, we can assume that sigma in this case equals 15, because we can assume in this case because it is a case where sigma is known, okay? And then we can use the formula 7.4. That means n, to calculate n is z alpha over 2 times sigma divided by e, and then square. We already have z 1.96, we already have sigma 15, we have e is 3, and we plug everything in here to calculate n. And we, please remember, we need to round it up, right? For this one, we use the round up formula, round up rule. It will be to the 97 instead of 96. Okay, we round it to the next whole number. And the interpretation in this problem, that means among the thousands of statistics students, we need to obtain a simple random sample of at least 97 of their IQ scores, right? With a simple random sample of only 97 statistics students, this is we will be 95% confident that the sample mean X bar is within 3 IQ points of the true population mean mu. So these are like the interpretations for this problem. Okay, so we still have some time. Let's do another example. Let me make maybe I'm gonna give you the example to show you about the bootstrapping method. Okay, the bootstrapping method. For example, if you oh, like this one. No, I don't like. I like the blank one. Okay. You have a small data set and want to estimate the population mean, but you don't know if standard assumptions hold. So the bootstrapping is a resampling method that lets you build confidence intervals without formulas. For example, I'm gonna give you the given one. We have the test scores 78, 82, 85, 90, 94, 87, 88, and 91. So let's do the following. We will follow all these steps. The first step, resample from the sample. Resample from the sample. What do you what does that mean? It means you can use technology like R or Python or Excel. We randomly draw samples with replacement from the original data. So each sample should have 8 numbers, right? Because in this case we have 8 numbers in the test score data here. And then after that we will repeat the resampling process many times. Repeat the resampling process many times. Usually, like we can do around 1000 or more times. For each sample, we calculate the mean, okay? And then the third step, we build a distribution of means. Build a distribution of means. This is called the bootstrap distribution. And the fourth step, we find the confidence interval. Interval. So in this case, for a 95% confidence interval, we take the 2.5 percentile and 97.5 percentile of the bootstrap means, and the result from the bootstrap we can get like for 2.5 percentile, it is 83.6, and the other one 75 97.5 percent tile equals 91.4. So we can do the interpretation because this is the lower bound, this is the upper bound, right? So using bootstrapping, we are 95% confident the true mean test score lies between 83.6 and 91.4. So in this case, I think we can use the Python or R code because we need to resample, right? And you need to calculate the mean like 1000 times. So it's better if you use the technology in this case. And if you need the code for Python or R, I'm gonna share it. I can share it to you. Let me check the. I can check the slide to see if we have it here. I'm gonna share it up here. Otherwise, like it's 7.3. Okay, we don't have it up here. 7.2. Okay, I'm gonna share the generate Python or R code to demonstrate the bootstrapping process to everyone later. You can use like import numpy, import this one. I think I can take the photo. Uh, I can share the screen real quick here so that everybody can see it here. Open, maybe open the blank one. Let me see if I can copy and paste it here. Insert new slide. Okay. Let me share the screen here real quick, and then when I record it, you can see it too. Uh-oh. It's weird because I imported and it's like out of the frame. Okay. But anyway, it's gonna be right here. If you use Python, you can import these two libraries, and then you use the original sample data, right? You can add the data here, and then the bootstrapping setting, you can do n iteration is 1000, correct? And n size, you can use the length data, calculate the length data here, and store the bootstrap sample min. You can store it in here. Bootstrap min equal this one. Let me move it down here so that you can see it clearly, right? And then you resampling with replacement. So you can use the loop for I in for this one you can do it in the range of any iterations, and then you can calculate the you can calculate and store. This is the step for resampling with replacement, and then you can calculate the 95% confidence interval using, this is the lower one, the upper one, and then and the output you have the lower level, the lower bound and the upper bound. Okay. So please try to use this one and practice that one. So we can do you have any questions before we stop recording or we finish the class today?
No, I was just going through the, just through that problem, but
Okay,
no,
yeah,
I don't have
okay.
any, no, I don't have any questions.
Yeah, okay. So if we don't have any question, I'm gonna stop recording here, and I'm gonna share this to everyone. Stop.